In this talk, I'll introduce data-driven hint generation algorithms in general and talk about the SourceCheck algorithm in specific. So these algorithms in general take as input a set of correct solutions that they use as training data. And we can represent these solutions in a solution space, which is shown over on the left. Now this is real data from the iSnap system visualized with an embedding. And in this solution space, we see a set of what we'll call traces. So these are individual attempts by a given student on a given problem. These traces are individual snapshots, which are themselves representative of a student's code at one point in time as they work towards a solution. Presumably, students start in the same starting state, which might be empty, and they work towards a set of solutions. And again, these are solutions because the input consists of correct, complete solutions. The goal of these algorithms is to take a second piece of input, a hint request, which we can represent as a partial trace through the solution space, which ends, rather than in a solution, in a hint request. So then the goal is to take that hint request and return to it a suggested next step, which we can represent as a subsequent snapshot or an edit to the student's code. Now there are two primary approaches that have been proposed. The first are graph-based approaches, which are based on the hint factory approach originally. And in approaches, we want to situate the student's code inside of the existing solution space and find the closest trace to the student's current progress. We match the student to a known trace that got to a correct solution, and then we want to direct the student along that known solution path that another student successfully completed. The second class of approaches are solution-based. And with these approaches, we for the most part ignore the trace of this, the students in our training data set and rather focus on only their submitted final solutions. We try to identify the closest submitted solution using some sort of distance metric, identify that target solution, calculate a path through the solution space, perhaps a path that we've never seen before, and bring the student towards that target solution that we already know is correct. Now, the first step in that path represents the hint we actually give to the student. SourceCheck, which I'll be talking about in a minute, is a solution-based approach, and specifically, these solution-based approaches tend to be one nearest neighbor approaches. So we're finding the best match and pointing the student towards it. Now, SourceCheck was specifically designed to address hint generation for open-ended programming problems, which pose a challenge for existing approaches for a couple of reasons. Graph-based approaches tend to rely on a well-connected solution space. And as we saw before, the solution space for many programming problems is not well connected. So we don't get the overlap among students that's necessary to direct a student down a well-trod path towards a solution. Solution-based approaches also tend to rely on distance metrics that are not well designed for programming, such as tree edit or string edit distance. And path construction tends to rely on test cases. So the SourceCheck algorithm uses a code-specific distance metric and path construction without test cases. And to explain why that code-specific distance metric is useful, if we consider two pieces of very similar code, let's say on the left we have a student's hint request, and on the right we have a potential target solution. Now these actually only differ by the order of the two statements, and in this case that order isn't actually important. If we represent the two abstract syntax trees, we can sort of assign each of these nodes to one of the code elements. And as we can see, these trees are fairly similar, with B and C simply being interchanged between the two. Now, with tree edit distance, we'd calculate the distance by first deleting deleting F, then deleting C, and then reinserting C and reinserting F, such that these two trees now match for a total distance of 4. The SourceCheck algorithm tries to deal with this difference by using a more code-specific distance metric that breaks a student's code down into hierarchical levels. So at the root node, it notices that A and A are equivalent, so it has no cost there. At the next level, it notices that B and C are simply interchanged, and so it creates one edit there. At the next level, rather than comparing all the children of B and C, it looks at just the children of C, sees that they're equivalent, and just the children of B, and sees that they're equivalent. So the total cost there is just 1. Now in reality, it's likely that the student may be missing code that's in the target solution, such as this node F here, if we were to take that away from the student's code. And there might be code that's in the student solution, but not in the target solution, such as the node D that we took away here. And these form the basis for the insertions and deletions that we recommend to the student in addition to the move that was identified earlier.